Swayam Prabha. Digital India. Educated India.
All right, let's get started. So far this week we have looked at optical properties of materials, and we have focused so far on naturally occurring materials, okay, dielectrics, metals, and so on. Okay. Now we want to focus on how we can engineer. Rather, we will see what are engineered materials. Okay, I'll explain in a moment what that is. Okay, the whole goal is one of the key goals of nanophotonics is to design the optical response in the way you want it. Okay, and to do that, we'll have to first understand what's the landscape. Let's look at the materials that are available to us. Okay, and to do that, I'm plotting the epsilon and mu in axis like this. So x-axis is my epsilon and mu is my vertical axis. Okay, so right now I'm not even bothered about the imaginary parts. Okay, we understand that epsilon and mu are complex quantities. By the way, when so far in the beginning, I said that mu, I'll always take it to be 1 in optical frequencies. Okay, the reason for that is, most of these materials never have a magnetic response. So that's why we didn't care. But in nature, you do have some materials with magnetic response. So I have these 4 quadrants. And if you look at most of the dielectrics that we have, or even metals also, they all fall on one single line. This is my mu equal to 1 line. Okay, so you can have materials like glass, silicon, and so on with different epsilons. Okay, you can also have metals which have a negative epsilon on this axis. Okay, so these are the usual quadrants of metals and dielectrics. Okay. In addition, we have some materials like alloys, copper alloys and things like that. These are magnetic materials, which are like iron, cobalt, and so on. If you make some alloys of it, you will have some magnetic response. Okay, so these 3 quadrants capture all the naturally occurring materials. So there are no natural materials available which exhibit a property of negative mu and negative epsilon. Okay, so in a way, it has some very interesting properties. If you're able to find materials with both negative and negative real and imaginary, negative mu and epsilon, we can find some interesting applications. Okay, and we want to look for that. We want to engineer that. In the nanophotonics community, I think starting with about 2000, there has been a lot of emphasis on this. Okay, at least for 10-15 years, it was very strong research going on. Okay, and we can get an idea of how to get these negative mu and epsilons by looking at the Lorentz oscillator. Okay, so far we looked at Lorentz oscillator only for the epsilon, but it is possible that you can create a Lorentz oscillator for even magnetic permeability. Okay, for mu as well I can create, and the same things hold. Okay, it's just that the characteristic resonance frequency might be different, the width of the resonance might be different, and so on, but you can in principle have this sort of a response. Okay, so I'm just showing you one of such, wherein the epsilon, let's say, is varying in this fashion, the imaginary part is going to be exhibiting a peak, and that could even be a peak in the imaginary part of permeability. So I can express both my epsilon and mu as complex numbers in this fashion. Okay, once we do that, we can study some interesting effects. By the way, what does negative epsilon mean? In this case, the epsilon is less than 0, right? Negative epsilon, what does it mean? Well, we already mentioned once, I think, that negative epsilon essentially means that the polarization is going to be opposite to the direction, out of phase with the electric field. All right. So what? Okay. The reason why we should care is, when we studied Maxwell's equations, I conveniently told you that n is going to be root of epsilon. Okay, but that was a simplification. The full refractive index is going to be square root of epsilon and mu. But in the optical regime, optical regime, mu equal to 1 typically, unless you actually go to some, you design structures which exhibit a mu of not equal to 1. In most cases, it's going to be 1 if you don't do much. Okay. So in that case, of course, n is going to be turning out to be root of epsilon, but that's not a general scenario. Okay. And the reason we find it interesting is because when you have materials with this engineered epsilon and mu, we call them as metamaterials. Meta meaning beyond. Okay, beyond the existing materials, that's why we call them metamaterials. Okay, so now what I can do is to get a idea of what this is. We are going to discuss them at length at some later point, but right now I just want to give you why this is important. Okay, how this is important, and the goal is to essentially create what is known as negative index. Okay, how do we do that? Well, if I give you numbers in this form, it's not a very easy, convenient thing to do or convenient thing to study. So what I'll do is I'll write out my the epsilon and mu's in terms of phasors. Okay, so I have my complex number. I can write it in a complex plane as we have real and imaginary parts. So I can write it in terms of a amplitude and a phase term. Okay, so for example, if similarly I can do the same thing for the mu. I can write it in terms of a magnitude and phase. So now what I'll do is I'll say that so far we have assumed that mu is always 1. There is no phase part, right? There is no angle into that. So from what we know, mu should always be here, mu equal to 1, right? This is what it is. But for a moment, let's say that there is some real and imaginary parts, and mu is like this. The magnitude of this is this green line and e power I phi, some magnitude term and phase term. Okay. Similarly, I can think of an epsilon which is in this case, the both mu and epsilon are plotted on the same axis, just to give you convenient representation. That's it. Okay. So now the epsilon I can still plot it as, let's say I can think of an epsilon of this form, minus, let's say minus 2 plus 0.3 I, something like that. If I do that, how will I represent it? Of course, minus 2, so it should be on the negative side, and there is some imaginary term. Okay, so let's say this is my epsilon, e power I theta. Okay, so I'm representing, of course the magnitudes can be different, but I'm normalizing them to each. Okay, the magnitude I'm always making it 1 so that I can put it on a unit circle. Okay, so now if I have such a scenario, what is my refractive index? So now I know my refractive index is simply root of epsilon and mu, right? So I'll end up with a refractive index which is some magnitude, which is dependent on the magnitudes of epsilon and mu, and I'll have a phase term which is essentially the average of both the phase of mu and epsilon. So it will be somewhere halfway between that. So if this was my mu and this was my epsilon, my refractive index is going to be in the blue here. So this is my refractive index, magnitude of n, E times I theta plus phi by 2. Okay, this is my refractive index. So we'll, instead of, I can make some statements about this, but instead of making those statements, I'm trying to motivate, how, we said that there is nothing like a negative index that is available naturally, and how we can realize that negative index is what I'm trying to get to. Okay, and by the way, this epsilon and this phasor, right, it's going to depend on frequency, because this is never going to be, a fixed amount. It's going to vary as a function of frequency. So at each point, you're going to get a complex number. All right, that is the dispersion that we talked about multiple times. All right, so what? Okay, the reason is, let's consider a few examples. Okay, let's consider a regular dielectric. Okay, in a regular dielectric, I know my mu is equal to 1. Let's say my epsilon is some number. Okay, let's say that some just 3 plus 0.2 I or something, real and imaginary parts. It doesn't really matter. Okay. So if I have a situation, how do I represent this in this complex plane? I'll say my mu is 1, so I'll put it here. And my epsilon also is, the real part is positive, so I'll have to put it somewhere like this. Okay. So my refractive index is going to be the average of these two, and that is going to be this. And, right? And something, some phase term, I power something, theta plus phi by 2. Right? So this is what it's going to be, refractive index. That means refractive index is positive. Okay, this is positive index, and absorption is not equal to 0. I mean, there's some absorption also because the imaginary term. Now in this case, I'm putting this as epsilon, mu, and all of them I'm representing on this. The real parts are here. Rather, I should not do that. I should do this real, and the imaginary parts are on the y-axis. N, mu, epsilon, all of them. Okay, this is what it's going to be. Now, let's think of a lossless metal. Okay, so let's think of same no magnetic response, mu equal to 1. Okay, but now a lossless metal, by which I mean that, okay, I should put it in, I think, red. Mu I have used right here. So this is my mu, and my epsilon I want it to be lossless. So epsilon is going to be some minus epsilon 1. There's no imaginary term. Okay, so if there's no imaginary term on the y-axis, it's going to be 0. So this should be the epsilon. When I have an epsilon like this, a mu like this, what will be my refractive index? I can have a 0 refractive index. This is my n, right? What does it mean that you have a 0 refractive index? Okay, think about the implications of it. What will be the velocity of the wave there? And so on. Okay, so basically here, n1 equal to 0, and 2 is not going to be 0. Some absorption is there in the material, of course. Okay. By the way, this 0 refractive index cannot occur at all wavelengths, but it can occur only when you meet this condition of a lossless metal, which we know is not possible practically. Okay, but just as an idea, right? Okay. So now, if you want to make sure that the refractive index goes in this direction, because that's where you can get a negative index, right? If you want to make sure that it can happen like this, we'll have to consider a material with a magnetic response. If you don't, you cannot get negative index. Okay, and so for a while in the metamaterial community, this was a big rage. People were trying to come up with geometries that have a magnetic response. All right, it had all sorts of other interesting applications as well. So now let's consider a material with some magnetic response. Okay, so now my mu is going to be of this form. Now it's not just 1. This is my mu e power I phi. Okay. So it has mu not equal to 1. Mu is not definitely the standard one. Rather, when I say mu equal to 1, I'm meaning mu relative. Okay, not mu 0. Mu 0, of course, it is what it is, right? This mu is essentially mu relative, and epsilon relative. Okay, by the way, it should be that. Okay. So now I can talk of, let's say, some epsilon. Let's say my epsilon is in this form. Okay, you have a material which is a metal with small loss. I have this scenario. If I have this scenario, what will be my refractive index? Excuse me. Now again, you just have to look at the angles and then you have to come up with a average. So it will be something like this, roughly. So my index now, n, right? n1 is negative. And of course, there is non-zero absorption. Okay. So if you want to have a material with negative index, okay, since we were talking about optical properties of materials, I thought I'll also introduce this fun idea of, let's say, negative index. I need to create a material with negative response and also preferably very, very good metal with low loss. The challenge is, if you have a stronger magnetic response, then you'll be able to have index which a good negative index material with low absorption. That's practically a very challenging thing to do, especially at optical wavelengths. People have done it at RF and microwave, and they see a lot of interesting effects. Okay. Later in the course, we will talk about how to engineer the optical response. So far, it's just an oscillator, right? We gave an example of a Lorentz oscillator where You have it in nature and you're just understanding it. But it turns out that you can actually make this happen. Even if it is naturally not there, you can engineer an electric response or a magnetic response. Okay. How do we do that? We will talk about it, a couple of weeks from now. Okay. But I just want to leave you with this idea that optical response, it is fundamental to understanding a lot of nanophotonics. And you have the naturally occurring responses, which we understand using various models. And we also have metamaterials, which are having engineered response. Okay. And if you run any simulations in nanophotonics, you will end up using these values of epsilon and mu and so on. Okay. And you need to be careful about what you're using. Okay. If you don't choose the right parameters in your simulation, the results that you get are actually not reliable. Okay. So I hope that, this week's lectures gave you an idea of what a material should look like. Okay. You got some insight into how they should behave. So hopefully tomorrow, let's say if you pick up some data, you understand that and what are the limitations of your simulation. Okay. Let's say if you're trying to capture a phonon. Okay. Let's say you have an effect because of phonon absorption. If you don't put the phonon absorption into your optical materials, you can never capture that, because all the simulators effectively solve the Maxwell's equations in various geometries. So if you do not supply the right Maxwell's equations, rather Maxwell's equations are always right, but you do not supply the right material properties in terms of epsilon, real and imaginary parts, and mu, real and imaginary parts, the simulation is not correct, isn't it? So we have to, this is a very critical element of nanophotonics. Many times, starting PhD students tend to neglect it, but if you do, it's not right. I mean, you see some research papers which are neglecting some of this. Okay, we should not do that. All right. So with that message, I'll take leave. So in the next week, we will actually talk about plasmonics, which is an interesting approach to nanophotonics. All right. We will deal with metals. So far in this lecture, we have talked about metals, right? We showed that how silver is a very low loss material. Gold is a comparatively low loss material. So we see that we can exploit some of these negative epsilon properties of these materials and engineer some interesting effects. Okay, we will talk about that in the subsequent lectures in the next week. Right. Thank you so much. We'll meet you next week. Bye.